This is part 4 of the video notes for Objective 4, Graphing Trigonometric Functions. In this section, we're going to be focusing on the graphs of tangent and cotangent. Well, tangent is one of my 3 main trigonometric functions, so I'd like to build this graph the same way that we sine and cosine, by creating a table of values. So let's consider the unit circle. Just like I did with sine and cosine, I'm going to use all values from the unit circle and their outputs for tangent. Unlike sine and cosine, I need to do a calculation for each tangent value unless I'm looking at a unit circle that has them listed. So let's start at 0. At 0, we have the ordered pair 1, 0 on our unit circle. Since tangent is sine divided by cosine, or y divided by x, I know that tan of 0 is 0 divided by 1. At pi 6, the ordered pair is rad 3 over 2, 1/2. If I do y divided by x, I get 1 over rad 3, which rationalizes to rad 3 over 3. At pi 4ths, the ordered pair is rad 2 over 2, which, when you divide y over x, you get 1. At pi 3rds, the ordered pair is 1/2, rad 3 over 2. When I divide, I get rad 3. Then at pi halves, the ordered pair is 0, 1, which is the first position that tangent is undefined for. So let's take a look at what that graph would look like. Creating my axes, I want to scale from 0 to 2 pi. And I'm going to keep my typical 0.5, 1, 0.5, 1 scale that I used when I was building the graphs of sine and cosine. Filling in a few missing values. I'm now ready to graph this function. Starting with the point 0, 0, pi 6, rad 3 over 3. Well, if I use my calculator, I can figure out a decimal approximation for rad 3 over 3, which is about 0.577, so a little bit more than 0.5. Then I have pi 4ths, 1. Then I have rad 3, and using my calculator, I can decimal approximate that to about 1.732, which means I do need to increase my scale up to 2. No big deal. 1.7 is about here. And then we reach our first undefined, which we've seen with secant and cosecant is a vertical asymptote. Well, what does tangent look like when you connect these dots? The tangent curve tends to appear, and I'm going to adjust that point, like this. And it rides up to the asymptote. We're going to repeat this process for the remaining points around the unit circle. All right, you may have noticed something as we were graphing it, but you also may not have noticed because the change is subtle. Tangent does not have the same period as sine and cosine. If you recall from graphing sine and cosine, it took the entirety of 0 to 2 pi to repeat values and cycle through the same information. Tangent only needs pi to cycle through and begin repeating values. At this point, it starts back at 0 and goes through the same motions that it did in the beginning. So what's important to note here is that the standard period of tangent is 1 pi and not 2 pi. This is going to affect all of our tangent and cotangent graphs from here on out, because as we calculate the period from the frequency, we no longer reference 2 pi over b, but pi over b. It's also important to note, because tangent has asymptotes, as we list our critical values, we would say 0, 0 and pi 0, but we have to list our asymptote, x equals pi halves, and every asymptote is pi away from the previous, like so. Let's take a look at a few more graphs of tangent as well as its reciprocal function, cotangent. Next example, we're going to be graphing tan 2x plus 3. Tangent, if you've noticed, does not really have an amplitude. It goes up to infinity and down to negative infinity at each section of its graph. Instead of focusing on the amplitude, which does affect the graph of tangent, we more pay attention to period, phase shift, and vertical shift. So in this example, the period is pi over 2, not 2 pi over 2. And we have a vertical shift of 3. What's that going to look like on our graph? Well, let's go ahead and label pi, 2 pi, pi halves, 3 pi halves, and let's count 1, 2, -1, and -2. The standard tangent graph starts at 0 and ends at its period, which is pi. But this tangent has a period of pi halves. So instead of ending at pi, we're going to end at pi halves. Halfway in between its starting point and its ending point, the tangent has an asymptote. Since tangent is a periodic function, we know that this pattern is going to repeat across the graph. What does tangent look like? Tangent begins positive in the first quadrant, negative in the second quadrant, and we'll continue this pattern across the graph. Now with the tangent graph, because my asymptotes are already dotted, I tend not to dot my sketch. Instead, I'm going to switch colors to indicate my final answer. The last thing I need to do to this graph is raise each of my points up 3. And because I didn't use any helper points along the way, there are points along the way that I could have used. I just want to make sure I get this sort of curved S shape between each asymptote. And that's the graph of tangent 2x plus 3. Let's compare our blue sketch, or my blue sketch, to what the calculator predicts. Looks about the same, which tells me that I have graphed this correctly. Let's try our next example. For this example, we're going to go ahead and try graphing tangent's reciprocal function, cotangent. To graph a reciprocal function, you need to consider the original function. Well, the original function, tangent, has a period of pi, begins at 0, and has an amplitude or an asymptote in between. So here's my original graph of tangent. How do I reciprocate this original graph? I turn every 0 into an asymptote. And every asymptote into a 0. Now the same quadrants that tangent is positive in, cotangent must also be positive because a reciprocal has the same sign as an original. But cotangent actually curves in the opposite direction as tangent. When tangent is increasing, cotangent is decreasing, and vice versa. So this is the graph of cotangent x. Let's check our sketch with what our calculator produces. To graph cotangent, we do 1 over tangent. We used a regular period and no shift. And again, our hand sketch matches what our calculator sketched. One more example before we talk about the role of amplitude in tangent and cotangent graphs. For this example, I've introduced a period change and a phase shift. And so we want to be careful that we're remembering to scale our information to tangent's period of pi versus 2 pi. The period in this example is pi over 2, and the phase shift is pi fourths to the right. With this, because the 2 has already been factored out of the pi fourths, I do not need to divide the pi fourths by the frequency. It's already been done for me. That's something that I'm going to need to remember each time I'm dealing with a phase shift and a period adjustment. Because the period is pi halves, it still fits on my 2 pi scale, so I'm going to keep the same scale that I've been using for every example, since it shows off the changes a little more clearly when your scale stays permanent. So to graph tangent, I know that it begins at 0, ends at its period, and has an asymptote in between. Asymptote in between, asymptote in between. For a phase shift of pi fourths to the right, I need to take each point and shift it 1.5 boxes to the right. Essentially, I'm trading every 0 for an asymptote and every asymptote for a 0. And finally, I need to graph my tangent in the direction I know it would have gone. Tangent begins positive, then negative, then positive, then negative. Last piece, and I've completed tangent 2x shifted pi fourths to the right. Let's go ahead and see what this graph looks like on our calculator. And it's the same. The last thing we want to discuss for this lesson, and to wrap up this lesson, is the effect or the role that amplitude plays in tangent and cotangent graphs. So on this sheet of paper, I am going to graph tangent x three tangent x and 10 tangent x. Generally, the amplitude represents how high and low the function can go from its midline. But with a function like tangent, whose range is infinity to negative infinity, this amplitude has to play a different role. Starting with tangent x, I know that it begins at 0 and hits 0 again at pi with an amplitude in between. And because the shifts are so subtle, I'm actually going to use my calculator for all three. I want you to be able to see the difference for yourself in how subtle it is. Tangent x, 3 tangent x, and 10 tangent x. See the difference? If you relate this back to what you've learned before, the closest example I have and I've been able to use is slope. The slope of the tangent graph becomes more steep. Actually, that one's even more steep than that, really, with each change that we make. And so the amplitude in the role of tangent and cotangent ends up to be the steepness, or how straight the graphs appear. This concludes part 4 of Objective 4, Graphing Trig Functions. At this point, we have graphed sine, cosine, tangent, secant, cosecant, and cotangent, applying amplitude, period, phase shift, and vertical shift. From here, it's just a matter of getting enough practice and using our technology to make sure that we can confidently and accurately depict each function.